Okay, Lagrange multipliers 14.8 literally take 19. This time we're not having any boo-boos though. We're going hopefully no problems. Okay, so I'm looking on here for my Lagrange multipliers. So I did have a typo on page 50 of your notes, and well, it wasn't so much as a typo as it was a really hard problem to solve, and I was like, oh my gosh, that's not what I was looking for. So I'd like to change this example to this one right here. Find the max and the minimum value for the function. So if I do that, then what I need to do is I need to find the first derivative. I hope I'm recording. I am. So this is x to the third plus 7 x to the second minus 8x. And what you need to do with that first derivative, right, the procedure for finding the min and the max is to set that equal to 0 and also find when it's undefined. So you want to know when is this 0 and when is that derivative undefined. And it's not undefined. So I'm just on the procedure, right? Calc 1, here we go. So I'm going to factor out an x. When I do, I get x squared plus 7x minus 8x equals 0. Factoring that, it's x plus 8, x minus 1, right, equals 0. So that gives me critical values of 0, negative 8, and x is 1. So then the next thing that I would do, right, if you're looking for the absolute max and the absolute min, is that you could find out what the value for f is. So for example, f at 0, if I plug that in right here, 0, 0, 0 is 0. And then if I put in negative 8, and I do the arithmetic there, so 0.25, I'm putting this in my calculator, that's 1/4, times negative 8 raised to the 4th, plus 7/3. I'll put it as a fraction because you can't do that exactly as a decimal, and at least I don't know how to put it in my calculator, negative 8, and so it's better as a fraction to the 3rd, whereas 1/4 didn't matter, minus 4 times negative 8, into parenthesis raised to the 2nd. Okay, so I get a really big negative value there. Okay, so this is, that's 2/3, right? So negative 426. I've never done that before. 26 and 2/3. Then f at 1. So if I put in 1, everywhere I had 8, negative 8, delete 1, delete 1, delete 1, I get negative 17/12, which I'm going to write as a mixed number. Makes it easier for me to see which one's bigger and which one's smaller and all of those kind of things. And then if I just said, well, okay, well, the very smallest one right here, that one right there, is the absolute min, is f at negative 8 equals negative 426 and 2/3. And if I said this would be the absolute max, f, the biggest one, f at 0 equals 0, well, I'd be wrong, right? And so this is why I wanted to show you this is, and I want to show you a graph so that I can show you why I'm wrong, and you can tell me what I did wrong as well. And if you're like, you led us astray, you're right, I did. I led you astray, and I would probably do it again. So this right here is what I'm looking at, and this is the graph of what I'm looking at, and I am way zoomed in. It's hard to zoom out on this one. I might be able to, that the plus doesn't do it. It's the home screen. No, it's not the home screen that does it. It's that here, yes. So on the X, I'm going to only go over here. No, that's perfect. But I'm going to go down here to like negative 500. And 599, how do I get that? And double negative 500. It's the Mac. You know, the Mac is back. And what was the highest on that? Well, let's just go ahead and go to 100. What the heck? That'll be enough for you guys to see. Maybe 1,000. Sorry. And that'll be enough for you to see maybe. And then, okay. And then I'll maybe center it just a little bit more and maybe just kind of move it around a little bit. Okay, so scaling had to get a little bit off on that just so that you can see. But definitely that value right there was the absolute minimum value. But if I was saying that this was the absolute maximum value, it's not true, right? If I was saying that 0, 0 was the absolute maximum value, it's not true, because here's 0, 0 right there, and you can see that there are lots of values that are higher up than it, infinitely many values, in fact. And in fact, if we're thinking about it, paper view, going to go on the paper view here, if I can get on the paper view. Click over here. Oh no, I hope I didn't click off something. Make something not work. I hope I didn't. I don't know. Let's see. The mic seems to still be working. I'm hoping, we'll be hopeful. Okay, the problem is that it didn't have an absolute max because it went up to infinity. And so this method wasn't really a good method for finding the whole picture. Now, it was a good method and would have worked had it been one that was guaranteed to have a maximum. And then when is it guaranteed to have a maximum? Well, it's guaranteed to have a maximum and a minimum by the extreme value theorem, not just local mins and local maxes, but an absolute max and an absolute min. And it's guaranteed to have them when it's continuous, which it was a continuous, so that wasn't a problem, on a continuous on a closed interval. And that was the problem. Is my interval wasn't closed. My domain was from negative infinity to positive infinity. If my domain had been from negative 9 to 3, then it would have had a maximum value, and I would have been able to use this method to find the maximum value, except for I would have had to also have worried about endpoints. And that's probably where the maximum value would have been at one of the endpoints. Anyway, I tell you this is because when you get going on these Lagrange multipliers, it's going to be a little bit more tricky to know for sure that you found the max and the min if you're not guaranteed to have one. And so anyway, but we're going to look at the procedure and then I'll show you that situation. So Lagrange multipliers, is anyone playing ZZ Top? I hope you are. It can be, because I can't play it because YouTube will strike this video. But Lagrange multipliers can be used to find the maximum or the minimum value of an object function, f, that lie on a constraint function g. And the idea is the max or the minimum values of the function that lie on the constraint are located where both the gradient of f and the gradient of g are orthogonal to the tangent vector of the level curves there. And what that means is the gradient of f and the gradient of g are parallel vectors, and that means they are scalar multiples of one another. And so if they're scalar multiples of one another, there's some scalar that you would multiply by 1 to make them equal to one another, and that scalar that they use in Lagrange multipliers is called lambda. And it almost looks like a fancy backwards h, or it looks like a fancy kind of an h. When I make it, it looks like this. And so when I kind of draw it along, I don't know, it's kind of fancy. And I always make it like this, and then I put a line straight down. And that's kind of how I go and make them. And then I get quickly making them and they look funny. But anyway, that's kind of how that goes. The method for f and g, both differentiable functions on a region R2 with the gradient not equal to the 0 vector, locate the max and the min values by taking these steps. Find lambda x, y, and y that satisfy this equation and that equation, and those are called critical points. Then list each of these critical values and find f at each of those criticals. And the largest is the max and the smallest is the min. And that's what our book leaves it at. And they don't mention anything else. And then one problem they had a little boo-boo on, and I'm going to show you that. But this is only true when your constraint equation is closed and bounded, because then you're guaranteed that you would have a max and a min. And when you list them, you could say, okay, the biggest one is the max and the smallest one is the min. And so anyway, so that would be the story. But if you didn't have one, if you didn't have a max or a min, it would be the same situation that I did up here, right? I went through this procedure, and because there wasn't a max, it was silly, right? And so anyway, and then they just go on to tell us that if, and I got this out of the Briggs book, of course, but if the constraint equation is an ellipse or a circle, then it's bounded, and then you'll have a max or a min. The same method can be extended to higher dimensions. Okay, so we're going to give a try to that. This is just in your book, and they're just trying to show you just a little bit what you're looking at. Here's our constraint function, and this is level curves of our function that we're looking at, and right here is where those are parallel to one another. And so that's kind of, we would say, okay, at 10, something's happening here. And so that's what we're kind of be looking at. We're going to be not looking graphically. The first example, we look graphically, but then after that, we're not looking graphically. We're going to be finding lambda, finding x, finding y, and trying it out. So this is example 1. This is actually a problem in your textbook. I don't remember which one it was. I can't believe I didn't say which one it was. But pictured are the contour map of f. And so this is a contour map of f. And they have and the curve equation where g at xy equals 8. And they want us to estimate the maximum and the minimum values of f subject to the constraint, that this is our constraint function, and explain our reasoning. So where we want to look is where they're as close as we possibly can to being just tangent to one another. And so like parallel to one another. On the ref, what does that mean? I think the blue is the plastic on the ref. What? My brother. Okay, and then if you don't respond, he'll come over. And so we have this place where that looks pretty well like their tangent right there. And I can notice that on the blue, they're at 30, right? So I have this 30 going. And then here, they're not quite tangent right there on 60. But if I did another level curve, right? So they've just done level curves by tens. And if they did another level curve like at between 50 and 60, closer to 60, then that would be the one that would just be tangent, that they would just meet right there. And I'm gonna say that one is at 59, is what I'm gonna say, ish. They said to estimate, and I have to estimate. So the bigger of these two is 59, so that is the max. And the smaller of these two is the min. So we did a lovely job on that. I want to look at this more practice with the idea. So I'm going to my MacBook screen, if I can figure out how to do it without ruining everything. And things haven't been going too well today for me. And so this is the picture of the level curves over here. And this over here is a graph of the function, and you can move it around, and I hope that you do. And when these are just kissing one another, that is when we're at the max. That's the highest. This is the gray is our curve the blue on there is our constraint. Over here, the blue is the constraint, and the red is our level curve that we're moving in and out and looking at. And so when they're just tangent to one another, when they just meet each other, that's when you should be at your very highest. I think that they're not exactly in sync here. They're pretty close in sync. Did you turn off? I think you might have. Um, and then if I go here, you can see that just as I hit tangent, I'm getting to the lowest. They're not perfectly in sync, like I said. They're pretty close anyway. I think my camera just turned off, and when I go back, I think, and I go to paper view. No, my camera didn't turn off. It did make a sound though, and that worried me. And anyway, so that's kind of the idea there, that the level curve, just where they're just kissing, and they were showing you that hey, you are at the very lowest on that constraint. So we're going to try some here and see how we do. I have a few examples. Is that you, camera, making sounds? Who's making sounds? Oh, it's my phone making sounds. My friend calling me, probably to say, would you like to have dinner? And I have more than one dinner plan already. I have two. Isn't that crazy? You could go weeks without dinner plans. I'm kidding. Anyway, okay, find the maximum and the minimum. And we have this function xy subject to, and I want you guys to notice that that's an ellipse. So since it's an ellipse, we're guaranteed to have a max and a min. And kind of what's happening, and I'm just going to draw this just to the best of my ability really quick, not getting too crazy on it, but I'm going to try to draw in here the axis 0 must be in the center between these two. And I'm just going to draw in an ellipse. I know that ellipse, if I solve it, if I got crazy and I solved it, you're saying don't get crazy, don't worry about solving it, don't show us what it means. Just get on with this example. Are you saying that? Why would you say that? Okay, so that's the ellipse that we have there. And so in the x direction, it's 4, and in the, square root of 4, which is 2, and square root of 2, which is like 1.4, something like that. So over here in the x direction, 2 and 2, and about 1.4 is precisely here because I'm really accurate. So we have this ellipse, and that's our constraint, and we're projecting that up, and we're saying, okay, where's the highest? We're projecting it up until it hits our crazy, that's our curve, right, our surface, until and we're just looking at, well, what's the highest value for z that is contained here. That's what we're looking for. Okay, so we're gonna give a try and see if we can. Let's see if we can find that. So here's our story. Because remember what we needed. We needed our gradient of f and our gradient of g. And do you remember that the gradient? Am I the only one that remembers? I hope that you remember that the gradient is the partials, correct? And so I need the partial derivatives. That you knew that with this is chapter 14. The answer to everything is find the partial derivative, right? And so we do need to find the partial derivative, and so that's what we're gonna do right now. So that's gonna be our strategy. And so here we go. Okay, so the partial derivative of with respect to x is equal to y, because we needed it. Get it? That's a joke on y. No, it's not very funny, I know. And then this is equal to x, right? And then we hadn't identified what g is, but that g is our constraint function. And so I'm going to write that right here just because I've written on top of that right there. So g at xy equals, and then 4x squared plus 8x y squared equals 16. And it doesn't matter if you move the 16 on the other side, because when you take the partials, um, or if you just said this is a level curve, whatever you did, because when you take the partials, the 16 is a constant, so that doesn't matter. So g at x is equal to 8x. G, the partial with respect to x of g and y, is 16y. Had a hard time saying that. So then we know that the gradient of f equals lambda. My fancy lambda gets to come out, and the gradient of g. And so the gradient of f is the vector at, partial of x, partial of y, so that's yx. And then this is lambda, and then same here, so this is 8x, 16y. So then we need to solve these equations is what we're going to need to do. And so what you want to do is you want to equate the components is what you're going to do to come up with some equations here. And so we're going to look at the three equations we need to find, and we need to find x, y, and lambda. So equation 1 is when I equate the x's. And so that would be y, the x component, y equals 8x lambda. Equation 2 is when I equate the y components, which would be x equals 16 y lambda. And then the third equation, and I have to find values for x and y and lambda that satisfy all three of these equations. The third equation is just our constraint equation, which was 4x squared plus 8y squared equals 16. So these are our equations. 1, 2, 3, 4, and 1, 2, and 3, not 1, 2, 3, and 4, but just 1, 2, and 3. And so we look at how to solve these, and I have to admit to you that I had done every single homework problem before I said to myself, I'm getting kind of good at solving these, or I'm getting where my algebra was thinking about how to solve them. And so it will take a little bit of doing before you get into it. And so don't worry about that. Just go with it. So if I trying to solve the system of equations, there's a lot of different ways of going. One thing that you could do is you could solve this equation for lambda, and if I wanted to at the same time, I could solve this equation for lambda if I wanted. And so when I do that, so this is equation 1, and if I rearrange it, it would be y over 8x equals lambda. And if I did the same to equation 2, that would be x over 16y equals lambda. And then I would know from looking at this that if lambda is 0, I just want to make sure that we kind of think about this. If lambda is equal to 0, I'm going to say that, then that would mean that would lead to y equals 0 from this equation here. And it would also lead to x equals 0. Those are what, if lambda was 0, it would lead to those two things, that y is 0 and also that x is 0. And I want you to notice that from equation 3, that cannot be true. So that tells us that our lambda has to be not equal to 0. So if lambda is not equal to 0, I just wanted to eliminate that case real quick because I could see that, hey, that's going to become a problem. Then I could equate these to one another. So that would be that y over 8x equals x over 16y. And then I could crisscross applesauce solve those, right? Cross multiply. So that's 16y squared equals 8x squared, which would mean that y squared equals, if I divide it by 16, equals half. 8 over 16 is half x squared. And now I can, so I've kind of put equation 1 and 2 together here, right? And I've created this other new equation, and where I plan on substituting that, what I've just come up with is into equation 3. And so, you know how you kind of have to put equations together in order to solve a system of equations. So we essentially put equation 1 and equation 2 together here, right? And we're saying to ourselves, lambda's not 0 in this situation. And now this is equation 1 and 2 together, and we're going to put that into equation 3. So we're going to have them all involved. So equation 3, 4x squared plus 8y squared. But what are we saying y squared is? We're saying it's half x squared. So I'm substituting into equation 3 what we just found from equation 1 and 2. So now I've got a blend of equation 1, 2, and 3 kind of going. And so this is 4x squared plus 4x squared equals 16. And when that's 8x squared equals 16. That's x squared equals 2, right? Dividing by 8. So that tells us that x equals plus or minus the square root of 2. And okay, wonderful. So now we know a value for x that could work. And then what I'm going to do is I'm going to plug that in back into equation 3 to find a y that works. And I really don't care about the value of lambda. I could go and find lambda, though, if you wanted. But what I really want to know is I want to know x and y. But I have to have an equation that works with x, y, and all of the lambdas. And so I'm going to find the x and the y. And if I find lambda, great. And if I don't find lambda, that's okay too. But you do need to find x and y. So then, back in equation 3, 4x, which is plus or minus the square root of 2 squared, what was it? Plus 8y squared equals 16. So if you square that, you get 2. Square a negative, you get a positive. Square a positive, you get a positive. So this is 8 plus 8y squared equals 16. And I'm trying to solve for y. So if I take away 8 both sides, it's actually going to be a little bit friendlier than x was. We get y squared equals 8. So we get y squared equals 1. So that tells us that y equals plus or minus 1. Okay, and we could find the lambda that goes with each of those. Like if x is the square root of 2 and y is 1, then what is lambda? We could find all of them. I think there's going to be 4 of them, but we don't really need to know lambda as long as we found x and y were good. And so now we kind of have these 4 values. And so now we're at the next step. So you want to find the critical values. And so we just found those critical values. X is plus or minus square root of 2. Y is plus or minus 1. And then we're on the list them. and find f at them, and the biggest one is the max and the smallest one is the min. So f at, and then so here I am listing square root of 2 and 1, both of them positive. And if you remember what f looked like, why don't I write what f is right here, because we're going to be testing an f. F at xy equals x times y. So we're going to have these four values, square root of 2, 1. So when I multiply those together, I get the square root of 2. And then when they're both negative, I get the square root of 2. And when one of them's positive, negative square root of 2, and the other one is, so we want one positive, one negative, get negative square root of 2. And other way, one positive, one negative. There's four values here. And so that's kind of what we get. And the outputs that we get, these two right here are tied. So these two right here are the absolute max. And these two right here are smallest. So they're the absolute min. And so we did a lovely job on that. And my concern before I set these equal to one another was that they could, I mean, I was going to get values for x and y, whether if lambda was 0 or non-zero. And so I just wanted to show you that, hey, the non-zero one, or when lambda was 0, should have been some answers that I should have gotten, but they didn't work out. And so anyway, so very good. Okay, so we did a lovely job on that. And then I went on the 3D grapher. My kids are home and they're laughing. I hate that when they laugh. I mean, having a good time, laughing. They did both. It took both of them to get my video going today. Was my cord. My cord is kind of, well, Tyler's ordered a new one because he's had to put it in such a strange angle to make it go. Okay, so this was my little twisty curve, and there's my plane kind of going there. And then this is the cylinder that came up and hit, right? And then I just put the 4 points on there so that you can see that those points are hitting at values that are maxes and mins. This one right here, just because of the way that it, when you have things in 3D, that one definitely looks like it's the highest, and over here, or whatever have you. But if you go and you put it on the geographer and you start moving it around, you'll notice, oh, okay, I'm looking at where it intersects is what I'm looking at, and the highest and the lowest points. Anyway, so that's kind of that story. And so it really, I'll let you do that if you want to go and put it in. Okay, so we're going to try this one. Hot diggity dog, you say. And so here we go. So we're getting a little bit used to it, I hope. So this is our G, which is our constraint. I just want to write it up here. And then what we're going to do, the process of doing the Lagrange multiplier. So we have this crazy looking curve here. And this thing right here is another ellipse. And so we have an ellipse here, and we're projecting that onto there. So kind of similar to what we had. So we are guaranteed a max and a min because that's an ellipse. And so here, the partial derivatives I go finding here. So that's 12x to the second, right? And this partial derivative is equal to 2y. And this partial derivative is equal to 4x. And this partial derivative, can you see what I'm writing? Yes, you can, is 2y. And then we want to come up with the equations that satisfy this, that are Our gradients are scalar multiples of one another. I forgot my lambda in there, but there's my lambda for my scalar multiples of one another. So I'm actually trying to solve this 12x squared 2y. That's my gradient equals, and then lambda times the g here, 4x 2y. And so I'm going to come up with equations. So this is equation 1 when I equate the x's. So this is going to be 12x squared equals lambda, let's say 4x lambda. And equation 2, 2y equals, equating the y's here, equals 2y times lambda. And then equation 3, which is your constraint equation, which was 2x squared plus y squared equals 1. Okay, so we did a lovely job on looking at that. Now, when I start looking at these equations to kind of go here, like if I look at equation 1, because it doesn't have x's and y's in it, it just has x's, I get 12x squared equals 4x lambda. So if I get 0 on one side, I get 12x squared minus 4x lambda equals 0. And if I factor out x's, then I get 4x, if I factor this, 3x minus lambda equals 0. So that tells us that 4x equals 0, or 3x minus lambda equals 0, not and, or. So this is x equals 0, or, and you could solve that if you liked for lambda. So this would be 3x equals lambda. Okay, so we kind of have this idea going on, and we're going to kind of follow each of these leads that we have. I also want to come up with here on equation 2. And I told you it took a lot of practice before I got the feeling of what I should do to try to solve these things. It's 3 equations, 3 unknowns, essentially, and but it's a little bit tricky. And there was a point when I even had a tear or two, if I'm honest, over thinking that, hey, I'm not able to solve these things. And then I got where I could kind of fish around on them a little bit and got used to a little bit of stuff. So this is 2y equals 0, or 1 minus lambda equals 0. So this is y equals 0, or now my brother's offering me dinner, if you can even believe it, which would be 3 offers of dinner, maybe 4 tonight. When it rains, it pours. So crazy. Okay, so we have those things here. This was definitely an or. So let's go here. Why does this take me so much more room when I get writing it for you guys than it did when I did it before? So let's say if x is 0, because that was one of my choices, right? So if x is 0, and if I go put this in equation 3, then this would be 2 times 0, so this is equation 3, 2 times 0 squared plus y squared equals 1, and that would lead us to that y squared equals 1, which would lead us to y equals plus or minus 1. Okay, so let's remember that on some values that we have. Then another for sure value, or another nice value that we had, was y equals 0. So let's try that one and see what happens. So if y equals 0, then putting that into equation 3, we get 2x squared plus 0 squared, is that okay, equals 1. Or that x squared equals half, which means that x equals plus or minus the square root of half, which is x equals, and I'm just going to use my calculator, square root of half. I'm not a peasant. I wouldn't leave it like that. Is square root of 2 over 2. So plus or minus the square root of 2 over 2. So we kind of have that situation going. Okay. Now, the other thing that we had was, on our OR, was that lambda equals 1, right? And if I use lambda equals 1, then if I go to equation 1 and look at that, that could mean that lambda 3x equals lambda, which could be that x equals 1/3. So if I use x equals 1/3 into equation 3, so let's see here, 2 times 1/3 squared plus y squared equals 1. So I'm just following that lambda equals 1 and going with, okay, if lambda equals 1, then from equation 1, that would mean that x equals 1/3. And then I'm putting that in equation 3. And so when I put that in equation 3, I'm trying to find my y value that would go there. So this is 2 times, and then 1 divided by 3 squared. So this is 2/9 plus y squared equals 1. So this is 1 minus 2/9. So that's y squared equals 7/9. And then if I take the square root, right, I'm running out of room here. I'm sorry. Y would equal plus or minus the square root of 7 over 3. Is that okay? I did that in my head. Square root of 7 over 3. Okay. And that goes with x is 1/3. So I kind of followed all my leads a little bit, right? I had kind of 4 leads. This lead here was at lambda equals, and then I used the x lambda's 1, and then kind of got. So I think I have all my leads kind of taken in consideration. And so what I want to look at is, well, what do all my pieces equal, right? As I list them out, and then the biggest one is the max and the smallest one is the min. So my equation that I had to start with was 4x to the third plus y to the second. Okay, so this was the equation we're looking at. 4xy equals 4x cubed plus y to the second. So if x is 0 and y is plus or minus 1, because it's squared, y is being squared, these are going to be the same. So I'm not going to list them as different cases because they would be the same, and they would be equal to 1. Do you guys agree that they would be equal to 1? Because 0, and then if I square this, I get 1. Okay, great. Now the next one is y is 0 and x is plus or minus square root of 2, but it's x to the third, so that's going to make a difference. So I'm going to have here f at square root of 2 over 2, comma 0. And what does that equal? And f of minus square root of 2 over 2. And what does that equal? Because they are not going to be the same. Like they're not going to be equal to one another like this one was. So I got to be short because I didn't have to write it twice because they were equal to one another. And so, is that okay? I hope it's okay. Otherwise, I'll just split them all apart and start circling them, right? And that would be fine as well. So this is 4, and then parentheses here, the square root of 2, divided by 2, raised to the third. Am I getting late for my one dinner date? Oh man, I'm gonna have to go without a shower. No, I'll have to hurry. and then have a shower, because that would never do. Okay, plus 0. So this is square root of 2. Do you guys agree that this would be negative square root of 2? Check it out. Oh, I can put it in my calculator myself. Right here, negative square root of 2. Okay, great. And then we have these other values over here. X is 1/3. And then y is plus or minus the square root of 7/3. And because the plus or minus is on the y's, they're the same. So let's see here. 4 times, and then in here I'm going to put 1/3. Out, plus, and then it's just y squared. So it doesn't matter if I put the plus or minus in there. I'll just put the plus in there. Should be the same. 3 in the bottom, and this should be squared. And that's 25 over 27. Oh man, 27. Okay. So we're looking for the absolute biggest, right? And the square root of 2 is around 1.4. 25 over 27 is less than 1, and that's 1. So the absolute max, and we knew there was going to be an absolute max, is the square root of 2. And the absolute min is f of the square root of 2 over 2, negative 0 equals negative square root of 2. Okay, so we had a lovely job on that. And these other values were not absolute max or mins. And so they were critical values. I don't know what they are. I didn't go find what they were, but I think we had a way of going and finding what each of those were, though. And so I think that we looked at that in the previous section. Okay, here's another one to look at. So it says find the max and the mins. Oops, sorry. Just checking you. Find the max and the mins of, and then it has, it's more, right? And subject to, and then it has more. Now, one thing that you can do when they have two constraint functions is that you can put them together, and that's a possibility to do. I wanted to show you not putting them together, but I could solve that for y, and then I could plug that into that, and then I would have one constraint function. And so do you see how I could put them together? And then I could do it the same way that I had been doing with just lambda, but I want to show you what you could do if you couldn't put them together. And so so if you couldn't put them together, this is what you would do. Okay, so I'm going to call this one g, which equals x minus y equals 1. I'm going to call the other one h, two constraint functions, y squared minus squared equals 1. And again, you can put them together. That's something that you can totally do. But I wanted to have the example of when you can't put them together. My mom is now worried. Everybody's worried. Yes. Call you later. Okay. And my brother can't going dinner with Tom. Okay, go. And then the rest is my book club. Goodness gracious, sorry about that. It's crazy. But they keep texting because they think something's wrong that I'm not answering. So I have to cut them off by saying something to them. Okay, so we're gonna do this. Where's my better pencil? Where did it go? How could I have lost it? Equals 2x, 2y, 2z. Okay, gx equals 1. G, the derivative of g with respect to y equals -1. And the derivative of g with respect to z equals 0. Then h x equals, that one's 0. The derivative of h with respect to y is 2y, and the derivative of z is -2z. Okay, then what we're going to be looking at when you have two constraints like this is your gradient of f equals lambda times your gradient of g plus, and then some other variable, scalar multiple thingy that you need. And they use mu in your book. So I'm going to use mu just right with them, and h. Okay, so there we have that. And then this is going to come up with a bunch of equations, and we have to find something that makes all of them true at the same time. So we have 2x equals equate. Ooh, I didn't write out my my thingies. That's going to be bad. 2x, 2y, 2z equals lambda times 1, -1, 0. Can you still see? Plus mu, and then h, 0, 2y, -2z. That 2 almost looks like a z. Okay, and so now when I start building equations, I'm equating the x equation here. So here I get 2x equals, and then lambda times 1, which is lambda, and then mu times 0, which is 0. Okay, equation 2, equating the y's. So this is 2y equals lambda times -1, so -1 lambda plus 2y mu. And then equation 3, equating the z's, 2z equals lambda times 0 is 0, and then mu times -2z, so -2z mu. And then we also have the constraint equations, x minus y equals 1, that's equation 4, and equation 5, y squared plus z squared equals 1. Okay, so now we're going to try to solve these equations kind of going along, and see how we do on there. So kind of as you look around, trying for something easy that you can solve, right? Or that you might be able to put together and solve. And so anyway, so that's kind of what I'm looking into. Do you guys see anything? Well, the easiest one to look at is equation 3. This, I'm like, well, I could solve it for lambda. This one has a lot of variables in it, but this one here, I think, so this is equation 3. As I try to solve these, and I told you that was the part that was the hardest, definitely, is to solve this 5 equations, 5 unknowns, coming up with ordered pairs x, y, and z in this case that solve all of them. And so this is going to be 2z, and I'm going to go ahead and add this to the other side, plus 2z mu equals 0. So this gets us 2z 1 minus mu equals 0. So that either tells us that z is equal to 0, or mu is equal to 1. Is that okay? And so if we go with, and just lead where this would lead, if z is equal to, so that this is true or this is true, right? And, or this leads to a set of solutions and that could lead to a set of solutions as well. Okay, so if z is 0, where is that going to lead us? So we kind of use this here. So let's start there. If z is 0, where does that lead us? Well, it tells us nothing about equation 4. Equation 1, it doesn't tell us anything about, or equation 2, but it will allow us to look at equation 3. And oh my gosh, all the lead fell out of that pencil. I can't believe that. It's kind of how my day's been going. So y, and then I break the little bit of lead. Oh my gosh, oh my gosh. Okay, I have to use a suckier pencil. So y squared, I'm looking at equation 5. Do you know what equation I'm looking at? No, because I did not say which equation I was looking at. Was this my pencil before? So this is equation 5. I get y squared plus z squared equals 1, but this is 0, right? So that tells us that y squared then would be equal to, y would be equal to plus or minus 1. Is that okay? So now, with that thought, I have to back up. I can't help it. I have to write y equals 1 or y equals negative 1, right? So now I have this situation going on. I'm kind of going around seeing what I have. So if z equals 0 and y equals 1, then in equation 4, x minus y, which is 1, will equal 1, and that tells me that x would equal 2. 2 take away 1. Do you guys agree? So now I have an ordered pair to check, and that ordered pair is 2, 1, 0. So I'm going to put the ones to check down here because I'm going to run out of room. And so I want to check, because here's my f. Hopefully I've gone low enough, but f equals x is 2, y is 1, 0. Okay, and we're going to check that. Now, if z is 0 and y is negative 1, then equation 4 tells us x minus y, which was negative 1, equals 1. X plus 1 equals 1 tells us x is 0. So this gives us, down here we go, x is 0, y is negative 1, z is 0. So that gives us something to check. Okay, so that kind of exhausts if z is 0. Doesn't it? Because we didn't know anything else, right, from that. So that exhausts z as 0. And now I would like to go on, well, what about if mu equaled, z is 0, we did that, and I got those points there, and I made a mistake here, right here, and I'm lucky that I was catching on with what I did yesterday. I haven't made a mistake on anything we've done, but right here where I solved this, I made a mistake. That should have been plus, and so that shouldn't have been mu as 1. It should have been mu as negative 1, and mu is negative 1. Okay, so now we're going to go on if mu is negative 1. Okay, so if mu is negative 1, okay, well, nothing about mu here, but mu's in this equation. Of course, this is equation 3 that we got this from. Mu's not in equation 4 or 5, so we would have to go in equation 2. And so it would be 2y equals negative lambda plus 2y times mu is negative 1. So this would be 2y equals negative lambda minus 2y. And then if we add 2y to the other side, we get 4y equals negative lambda. Okay. So I'm going to put this together because I got two unknowns in this silly thing. In fact, let me write this as negative 4y equals lambda. And I'm looking back here. This is already using equation 3, right? Because that's where we got mu is negative 1. This is now involving equation 2. And so I'm going to invoke equation 1 here as well. So this would be negative 4y. And what was lambda from equation 1? It was 2x. So now I got this crazy equation here that is telling me that negative 4y equals 2x. And I can choose to solve that for either x or y, my choice on that. If I go ahead and solve that for y, I guess that's what I would typically do, and I have y in the other two equations, so maybe that's the thing to do. So y would equal, if I divide by negative 4, that would be negative half x. So this is just the rabbit hole I'm going down from mu is equal to negative 1, right? I went with equation 2 here, and right here I got equation 3 involved. No, equation 1, excuse me. Equation 1 involved, because that's what lambda was equal to 2x. And I've come up with this equation right here, which I'm thinking about putting in equation 4. And so now I'm going to just kind of come up here, and now I'm going to evoke equation 4. Equation 4 is, my phone is just going crazy, x, and it's like, how can I be so popular? Well, it's because it's Saturday afternoon, probably. X plus half x, which equals to 1. And so this is 1.5 x, which is 3 halves, equals 1, or x equals 2/3. Okay. So if x equals 2/3, then we would know that y, please pencil, really? How many pencils have I had to go through here? Y would equal 1/2 x, so negative 1/2 times x, which is 2/3. So this would go with negative 1/3 would be y. And we would want to know what z is as well, right? And equation 5 would tell us what z is. So if y is negative 1/3, then that would be negative 1/3 squared plus z squared equals 1. So that'd be z squared equals 1 plus 1/9. 1 plus 1/9, because that's what 1/3 is, right? Which is 10/9. So z equals square root plus or minus square root of 10 over 3. Oh, I'm sorry. I'm really tired. And with my phone blipping off and on, I made a boo-boo. Have I used that boo-boo anywhere else? I hope I haven't. Equation 5. Have I used equation? I've used equation 4. I used equation 5 here, but I'm lucky because this was a plus. I wrote a plus. It was a minus from the beginning. Do you guys see how I made that typo? It was a minus from the beginning. So now I'm tracing where did I use equation 5. And I used it right here, but I got lucky because I was putting in z as 0, so I didn't make a mistake there. Right here, I was using equation 5 for the second time, and then looked, cheated. Noticed what I had earlier. I'm not going to go with cheated, but looked at what I had earlier and realized, without anyone to help me with my algebra and my typos, right? I made a mistake when I wrote down the equation. I mean, that's, I'm going to try to justify that could happen to anyone at this point, but this is not real. Okay, so all of that effort that I went to find that value, right? When mu was equal to -1, this would have been a good value, but it turned out not real. So I only really have 2 values, and these are the 2 values, right? And here's what f equaled. F x y z equaled x squared plus y squared plus z squared. And at 2, that's 4, and 1 is 5. And at zeros here, and -1, this is 1. And so it seems reasonable, right, to say, well, that I only had 2 critical values. This one be the absolute max, and this one would be the absolute min. But here's the problem. You knew there was going to be a problem because I told you already from the beginning that there was going to be a problem. And here is the problem. I'll make it brief. The problem is that I got so intrigued with the method that I forgot to look that this is not a circle or an ellipse. This is not bounded. Y squared minus z squared equals 1 is a hyperbola. And so because it's not closed and bounded, we're not guaranteed of having an absolute max and absolute min. And so I did this problem. It's problem 20 in your book. I got this answer. I said this was the absolute max. I said this was the absolute min. I put out a video on it. And one of my clever students from last semester shot me an email. And he said, remember your constraints. My constraints were x minus y equals -1. And the other constraint was y squared minus z squared equals 1. And he said, what about this value? F at -1, -2, and square root of 3. Now that's a value he just pulled out of his hat, right? But he said, look, it meets your constraints. So this is our x, and this is our y. And he's definitely right. It meets my constraint, right? Because if I put in there -1, subtract, and then -2, I definitely get -1, -2. Was that supposed to be 1 or -1? That was supposed to equal 1. I definitely get 1. And I typed it over. I made a typo, right? I definitely get 1, which is what we said here. And then if you take y squared, so -2, and you square it, and you minus, and you take the square root of 3, and you square it. The dogs in the neighborhood are barking. You get 1. And so this meets both constraints. This is an ordered pair that meets both constraints. And he says, then if you look at, well, what is f, x, y z, right, which is x squared plus y squared plus z squared. So this is definitely on both constraints. And if you look at, well, what output do they have? Negative 1 squared plus negative 2 squared plus the square root of 3 squared is equal to 1 and 4 is 5 plus 3, right, is 8. And that's bigger than 5. And so he's like, what the heck? And so I was like, what the heck? And then I asked Arnie, and then Arnie was like, well, it has to work. There's none in our book that don't work. And I said, yeah, no, this is I have the answer that was in the back of the book. Well, it was on the, was in their solution guide. And so what's the heck? What's the deal? So I started reading in every single book that I could. And then in Briggs, I read that, well, if you have a hyperbola, like I do on this one, that you're not guaranteed an absolute min and an absolute max. And so this value right here is not the absolute max, and there would have to be more. You would have to look into it more. And your book, Stuart says it's really difficult. And Briggs even said it's very difficult when this happens, when something like, to know that, hey, that there wasn't one. Now, it wasn't really difficult in our 2D example, right? I mean, I purposely tricked you on the 2D example by leading you along and saying, remember, this is how you do it, this is how you do it, and tricking you into not thinking, hey, there isn't necessarily one. Anyway, so you would have to go into looking at the graphing and those kind of things. It turns out if you do that, and you can go and graph this if you want. It was kind of difficult even to see then. It turns out that this one actually only has an absolute min, and it doesn't have an absolute max. My clever student named one value that was bigger, and if you're clever, you can name more points that meet this condition that have bigger values, maybe even bigger than 8. And so anyway, so that's kind of the story on that. If you're worried that, that, hey, she's going to do that to us on a test, I don't think that they intended to do that in our textbook, that I don't think they intended to have one like this. In Briggs, they go over it and they have a few. And they tell you, hey, be careful, beforehand and whatnot. And so don't worry, I'm not going to do that to you. I'm going to give you one that's a circle or an ellipse. Okay, so video over, pray it worked.